Hey everyone, this is Dr. V. I hope you guys are doing okay, learning about balancing, counting atoms. So in this video, we're going to go over chemical reactions and the law of conservation of mass, which you kind of already talked about a little bit. So this may be a little bit of a review just to kind of catch up and see where you're at. So the very first part here is talking about chemical reactions or chemical changes. So what's happening when there's a chemical reaction? Remember, with the law of conservation of mass, we talk about how mass can neither be created nor destroyed. It also doesn't pop out of nowhere. It's not like magic. It just shows up. There's reasoning behind it. So during a chemical reaction, total mass of products is equal to the total mass of reactants. The number of atoms on the left side should equal the atoms on the right side. So again, don't forget, even though this is blue, you should still be annotating this and highlighting it with the key words. For example, I would have highlighted how the number of atoms are the same on both sides, how total mass is equal as well. And this is kind of a neat summarization of that. With a chemical reaction, you have the reactants on the left, kind of like your ingredients. And you have that big number, the coefficient. Remember, that big number is what you can change in a balancing reaction. You cannot change, let me see if I can write. Remember, you never change this, ever, ever, ever. That just comes with the compound. And if it's ionic, like for example, like aluminum +3, chlorine -1, right? When we crisscross, the formula is AlCl3, right? And that's where that 3 is coming from, the fact that you crisscrossed. But if you're balancing this, you don't change the subscript. You would just add a coefficient. So remember, this is the only thing you can actually change here. Remember, the arrow tells you that it's producing or yielding or making, and making, of course, your products, which is if these are your ingredients, this is your final product, what you made. And again, now you have a model down here of that. So you have 2 hydrogen molecules. So there's your 2, there's coefficient 1, coefficient 2, plus an oxygen molecule. Remember, this is a diatomic. These are part of your diatomics. That's another 1 coefficient. And these are units. Like, you can't break these apart and say, I only need 1. No, you need the whole thing, because remember, this whole thing you can't change. That's how it comes. And so if you were to kind of play with these, like if they were chips or something, you would make sure that they're still proportional, right? You have 2 hydrogens for every 1 oxygen. And so that's how we get the 2 here. So be prepared to work more on this, because a lot of your questions, especially in the pre-AP classroom, and quizzes and tests, are more on the particular diagrams. So not only will you be asked to balance the equation, you actually have to model it using some type of images. Let's see if I can move. So exit that. And then lastly, what we're kind of working on with this now is the word equation. So how do you say this in words? So for example, here you would say I have 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. And you could also say it in grams as well, but that we can focus on later. So if you look at the back of your paper called Chemical Equations, number 1 through 7 is kind of like a review, so I'm not going to go over that in this video. If you go to Schoology actually and you go to the Friday folder, you'll see some links that I put up there for signs of a chemical reaction, reactions that absorb or release energy, so you can just kind of skim through those if you forgot something about that. But one thing I will help you in is 8 through 19. So let's see. So now actually, you can try 8 through 13 by yourself if you want to stop the video for a little bit. All you're going to do is you're going to use your knowledge of chemical formulas that we've been doing and symbols to show how each of the following will be represented in a chemical equation. So for example, just to start you off, and then I'm going to pause for a few seconds. Snowflakes. So because you probably haven't experienced that maybe, snowflakes would be water. So you would say it's H2O right? But in what form is water? If it's a snowflake, right? It's either solid, liquid, or gas. So I'm going to say solid. I'm going to write S. And that's it. Now, if the snowflake was on the ground and it was saying melting, then that would change. It would not be solid anymore. Okay. All right. So you can pause the video and you can try 9 through 13 on your own. Because that's actually what I would do if I was in class with you right now. And then check your answers. And the reason I say this is it helps you with learning rather than just watching me do it. If you try it first and then check your work after, then that works. Then if you want to fast forward to see the answers, you can check it. But I'm not forcing you to watch every single second of this. If you think you got it, you can just fast forward. So again, you can pause right now and do it, or we can move along. All right, so I'm going to continue on here for those that just want to keep going. So potassium chloride. Okay, as soon as I see a name like that, I should be writing down the symbols and the charge, potassium chloride. So that actually just cancels out. So that's going to be KCl. And it says melted, so I know that's going to be liquid. Whoops. All right. Oxygen gas, we just looked at that. Remember, oxygen is one of your diatomics. If you're like, what the heck are you talking about? Remember in the previous video or previous day, we talked about Brinkelhoff. Let me write that. In fact, that's how I remember it. If I can Brinkelhoff. Those are the 7 diatomics. They always exist as a 2 if they're by themselves. So this would be O2, and it's a gas, so I would just write G. Okay. Now, if you actually look at the periodic table, it also makes kind of a 7. If you didn't catch that on the video. Let me see. Exit the drawing. I'll get back to this. Okay, so crystals of copper 2 chlorides. Okay, so that's positive 2. Whoops. Positive 2. And chlorine negative 1. Whoa. Okay. So crystals, so it has to be solid. So if you were to crisscross these, it'd be copper chloride like this. Copper 2 chloride, sorry. And with solid. Okay, mercury at room temperature. So mercury is Hg. I believe at room temperature it's liquid. Correct me if I'm wrong later. I'll check that later. Water solution of sodium sulfate. Sodium is +1. Sulfate, remember, is one of your polyatomics that you should have memorized. Is -2. So that's Na2SO4 because you crisscross. And it's a solution, so it'd be liquid. So it's not that bad, guys. Don't overthink it. Don't overthink these. More often than not, you'll get it right rather than wrong. Whoops. Okay. So number 14, we're just translating a word equation into actual symbols. It says do not use any words because it's already in words, so we're trying to go and not do words. Solid carbon, so just like we did here, it's just literally C with an S. Burns in oxygen gas, so I'm going to add plus O2 gas. Those are the key words, to produce, so that means an arrow is coming. Carbon dioxide gas, remember that's a covalent compound that we learned about. It's linear, if you remember that, gas, like that. And then we just check to see if it's balanced. Well, the carbons are good. There's 1 of each on each side. There's 2 oxygens on each side, so I'm good. That's it. That's as easy as it's going to get. We're just translating it pretty much. So you can, if you want to pause and try the next one, go ahead and do that, and then You can check your work after. All right, so let's check this. If you decided to pause and come back, welcome back. If not, we're just continuing on. So carbon disulfide. So the fact that it has a di tells me it's covalent. So I don't even have to do any crisscross. It's just carbon disulfide. And it's liquid, so I'm going to do L for liquid. Reacts with, that's a key word. This is going to tell me it's a pot, like I'm adding it with oxygen gas, which again, we already know that. One of our diatomics. To produce, there goes the other keyword. You always kind of want to underline and see what the keywords are. Carbon dioxide gas, so that's easy. We just did that. And, so the word and in math as well just means to add. Sulfur dioxide, another covalent compound, SO2 gas. Now let's see if everything's balanced. I have one carbon on each side, so that's good. I have 2 sulfurs on each side. Oh, no, I don't. This one has 2 sulfurs. This one has 1, so I'm going to add a 2 here. And that changes my oxygens to 4, 5, 6. So how to make a 2 to a 6? Well, I'm just multiply this by 3. And that's it. Remember, you always want to leave the hose at the end. So you leave oxygen for the end. I always leave that towards the end. Is combustion burning reaction exo or endo? Remember, with burning and combustion reactions, it's going to be exo. You're releasing energy. You feel that heat around. Let's skip 17. Okay. So the last thing is, how do we go from this to words? Well, we've already done it, actually. You've already done it. When we were going from formulas to naming, and we did that for like 2 or 3 weeks, you were doing that already. The only thing that we're adding now is the keywords for adding, for making or producing something, and whatever's in the little subscripts. So remember, AQ stands for, I'm going to write this down somewhere. AQ stands for aqueous, meaning that they probably put the salt, like a solid, with water and they mixed it, and that's what that is. So like here, silver nitrate, they probably had the nitrate as like a solid and they put water in it along with silver and it made that. So you could say, you literally could just say aqueous. I wonder if I could type. It'd be easier to type. Yeah. Aqueous silver nitrate. Remember, there's no silver is the one that doesn't need Roman numerals because it is doesn't need the Roman numeral. It only exists as silver one. Aqueous silver nitrate, and right, to talk about this here, and whoops. Sorry guys, I'm trying out a new system here. Let's just start over here with this. Okay, I'm just gonna keep going straight before it messes up again. So aqueous silver nitrate and sodium, and aqueous silver, not silver, sodium chloride, right? That's the first two reactants. Produce, or you could say, you could also say yields, makes, produces, aqueous silver chloride, and aqueous sodium nitrate. Remember, you have that pink sheet that I gave you that has all the polyatomics. It has charges, how to name things, because right now the expectation is that you already know how to name. The only thing you're learning now that you're adding on to your learning is, the little subscript. What does the aqueous stand for? Make sure you say it. Make sure you have the keywords for addition and producing. So try number 19. Again, you can pause the video right now. And if you're back after pausing the video, now we're going to check number 19. So let's see if you got something similar. So here now we have a solid. So I'm going to say solid zinc. Oops. And aqueous hydrochloric acid. Remember, it starts with an H, so it's a hydrochloric acid. I do not need to say that it's 2 molecules of hydrochloric acid, although no, we don't. If somebody were to read this, they would have to balance it anyway. Like, balancing is just common. Like, if you have an equation, you know you have to balance it. So you don't have to tell me that I have 2 molecules of hydrochloric acid unless you really want to. Produces, or you could say, you know what, I'm going to just choose something different. I'm going to say yields zinc, aqueous zinc chloride. Remember, zinc is another one that doesn't need Roman numerals. It only exists as +2, and hydrogen gas. Remember, it's one of our diatomics. That's it. So, yeah, let me know if you have any questions on this stuff. It's not that bad, guys. Don't overthink it. It's pretty fun. We're getting to the really fun stuff in chemistry. So when we're back, we'll learn a little more about types of reactions.